The tallest elevator ever designed would pass the top of the Burj Khalifa in less than a minute and then keep climbing for 8 days. Japan wants to build this space elevator 96,000 kilometers above Earth, almost a quarter of the way to the moon. Its cars would carry up to 100 tons into space without a rocket. Obayashi, the company behind Tokyo Skytree, wants it operating by 2050. And on paper, the idea actually works. So why hasn't anyone started building it? Because this entire megastructure depends on one part nobody has ever made at full size. If engineers get it wrong, the largest structure in human history could tear itself apart. So, can we really build a space elevator? Well, to understand why anyone thinks this could work, let's go back to 1895. The Eiffel Tower had stood in Paris for only 6 years when Russian scientist Konstantin Tsiolkovsky imagined extending a similar structure all the way to geostationary orbit. There was an obvious problem. A tower that tall would push its entire weight toward the ground. Its lower section would buckle and collapse long before the top reached space. Then, in 1960, Soviet engineer Yuri Artsutanov turned the idea upside down. He proposed placing a structure in orbit and lowering a cable from it toward Earth. American engineer Jerome Pearson refined that design in 1975. He made the cable thicker around its most heavily loaded section. Arthur C. Clarke later introduced the idea to millions of readers through his 1979 novel, The Fountains of Paradise. That change made the modern space elevator possible on paper. It wouldn't stand on Earth like a tower, it would hang above it, under tension. The lower end of this cable would meet Earth somewhere along the equator. Now move 35,786 kilometers upward. At that height, we reach geostationary orbit. A station here doesn't actually hover. It travels around Earth once every 24 hours, matching the planet's rotation and remaining above the same point on the equator. Below this height, gravity pulls the cable toward Earth. But the section above geostationary orbit rotates around the planet too. Its motion pulls the upper cable and counterweight outward. So engineers extend the structure far beyond the station until that outward pull balances the weight hanging below it. Obayashi's cable reaches 96,000 kilometers. Other designs stretch to around 100,000. The anchor on Earth doesn't carry the full structure. It simply holds the bottom in place while the cable remains stretched from above. The greatest tension builds near geostationary orbit. And because the cable hangs from space, crews have to begin construction up there. Rockets would first carry a construction spacecraft and a tightly packed seed cable into low Earth orbit. Electric thrusters would then move the spacecraft gradually outward until it reached geostationary altitude. From there, engineers would unroll the cable in 2 directions at once. One end would descend toward Earth while the spacecraft moved farther into space, keeping the whole system balanced. Obayashi estimates that this process would take around 8 months. Eventually, the lower end would reach the equator, and the construction spacecraft would continue to approximately 96,000 kilometers and become part of the counterweight. At sea level, crews would connect the cable to a floating Earth port measuring roughly 400 meters across. Operators could move seawater through ballast tanks to adjust the cable's tension. They could also shift the platform within a limited area to avoid dangerous weather or a predicted collision in orbit. But the first ribbon reaching Earth would still be extremely thin. It couldn't carry a 100-ton elevator car yet. So the first job is to make that seed ribbon strong enough to build on. Crews would attach a small construction climber to it. As the machine traveled upward, it would carry another strip of material and fasten it alongside the original ribbon. The next climber would add another layer. Obayashi's plan repeats this process roughly 500 times. Each trip makes the tether strong enough to carry a slightly heavier machine until it can finally support a 100-ton climber. Electric motors would drive those full-sized vehicles. Solar panels or energy beamed from Earth could provide the power. Even then, nobody would press a button and arrive in space 30 seconds later. Reaching the geostationary station would take around 8 days. During that climb, Earth's rotation would gradually give the vehicle sideways speed. Cargo released at the right height could enter orbit, carry it farther outward, and that extra speed could help send it toward the Moon or Mars. But every climber would add more weight to a ribbon already carrying thousands of kilometers of itself. This is where the whole plan runs into its biggest problem. Every meter of cable below geostationary orbit pulls on the material above it. By the time we reach that section, the tether carries an enormous load. Steel can't handle it. In one simplified design, the stress would exceed steel's practical strength by more than 60 times. Making the cable wider sounds like an easy fix, but extra steel adds extra weight, so the problem grows with it. Engineers would taper the tether instead. It would remain narrow near the ends and become thicker around geostationary orbit. Even then, they need a material with roughly 30 to 50 megajoules of specific strength. Basically, it must carry an extreme load without becoming heavy itself. Carbon nanotubes, graphene, and boron nitride nanotubes can reach that kind of strength in tiny laboratory samples. Scaling them up changes everything. Manufacturers have to join billions of microscopic structures together. Misaligned atoms and tiny defects create weak points, causing the finished material to lose much of its theoretical strength. Researchers can already produce long graphene sheets. They still can't manufacture one continuous tether-grade ribbon with the same strength across anything close to 100,000 kilometers. So, the missing piece from the hook is the cable itself. The strength exists at a microscopic scale. We still don't know how to turn it into the largest structure ever built. Even if manufacturers solve the material problem, the climber creates another one. At the equator, Earth already carries the vehicle east at roughly 1,670 kilometers per hour. As it climbs farther from the planet's axis, it needs even more sideways speed to keep rotating with the cable. The tether gives it that speed. In return, the climber pulls the structure slightly backward, causing the cable to lean and send waves along its full length. Now imagine several loaded climbers moving at once. Operators would have to schedule each departure and monitor the cable's shape constantly. Thrusters near the counterweight could correct larger movements, while the ocean platform and active dampers help control the lower section. People would also spend days moving through Earth's radiation belts. Extra shielding adds even more mass, so the first working climbers would probably carry cargo. And even with no vehicle attached, the cable still has to survive everything between the ocean and deep space. Near Earth, strong winds would keep pushing the lower cable sideways. Lightning could strike the ribbon, while salt water slowly attacks equipment on the floating platform. Higher up, highly reactive atomic oxygen can erode exposed surfaces. The tether would also face ultraviolet radiation and huge temperature changes as it moves between sunlight and darkness. Then it enters Earth's debris field. ESA's 2025 report estimates that more than 1.2 million larger than 1 centimeter objects currently orbit Earth. Over 50,000 exceed 10 centimeters. A space elevator would pass through those crowded altitudes every day. Operators could track the larger objects and adjust the tether through movements at its anchor or counterweight. Smaller fragments remain much harder to see. That's why engineers favor a wide ribbon or several connected strips. If debris cuts one section, the remaining material could hold the load while robotic climbers carry out repairs. A complete break becomes far more serious. Cable below the break could fall toward Earth. The upper section may enter another orbit or move farther into space, depending on where the failure happens. An ocean anchor keeps the lower cable away from cities, but it can't remove every risk. So this would never become a structure engineers simply build and leave alone. They'd have to inspect and repair all 96,000 kilometers for as long as it operates. And before engineers attempt that system on Earth, they may test it somewhere with much weaker gravity. the first real space elevator may begin on the Moon. In October 2018, JAXA deployed Shizuoka University's STARS-Me experiment. It used 2 tiny satellites, a planned 10-meter tether, and a climber measuring just 3 by 3 by 6 centimeters. Compare that with an Earth elevator stretching nearly 100,000 kilometers. The Moon makes the problem much easier. It has only 1/6 of Earth's gravity, and there's no atmosphere creating storms, lightning, or powerful winds. Instead of reaching geostationary orbit, a lunar tether could stretch toward an Earth-Moon Lagrange point where gravity and orbital motion help keep it balanced. Some studies suggest materials we already manufacture, including Xylon and carbon fiber, may be strong enough for certain lunar designs. Engineers would still face micrometeoroids, deployment problems, and an enormous bill. But they may not need the near-perfect material that an Earth elevator demands. So, can we really build a space elevator? We understand how it could balance, how climbers could move along it, and how crews might. Also, subscribe to the channel if massive builds and impossible engineering are your kind of thing.